Okay, so this group is very not finitely generated. And in particular, there's just all kinds of stuff inside of this group. So if you just think, so I'm drawing in this box, I'm just drawing the graph of a homeomorphism. And I also put sort of dotted the line for the homeomorphism that is just the identity map, because I want to get some sense of, is it going up, is it going down? Okay, but pick any real number r you feel like. Any real number r. Pick any number you feel like, s, that's between r and 1. And then do that. Right? There's just, I mean, so there's already uncountably many, and all I've done is 2 pieces so far, right? I mean, this is a big group. This is a very not finitely generated, really not finitely presented group. Okay, so if I want to do anything with an algorithm, I'm going to have to consider finitely generated subgroups of this thing, not the whole thing. Okay, so in particular, there's one very famous finitely presented subgroup of PL plus I called Thompson's group F. It's a subgroup where all of the slopes are power of 2. So here I've got 2, 1, and a half. And all of the breakpoints, meaning where you're going to change your linear piece, are in the 2 adducts. The 2 adducts being any rational number whose denominator is a power of 2, and numerator is anything you want. Okay, there are 2 particularly special elements of Thompson's group F. They're always called x0 and x1. I don't know why. Well, because there's an infinite generating set that's x0, x1, x2, and so on forever, but why they're always x's in every paper, I'm not really clear. Anyhow, I'm only ever going to care about x0 and x1 in this talk. But I wanted to give you some sense of what they looked like. And I will point out to you that if I think about, so in some sense, some of the theme of what I'm going to be talking about later in the talk is that we really want to care about where the pieces of the graph that are not along the diagonal, not along the identity. And I want to just point out that if I took this over here and put its graph on the same place, they would, the place where they have support, where they're not on the identity, lands at the same place on one end, but not the other. And so that's going to be relevant in a while. Okay, so there are lots and lots of ways to represent an element of Thompson's group, or PL plus I for that matter. What do I mean by represent? Well, for those of you who saw my workshop yesterday, the real question in my mind is, how am I going to present this to a computer? Right? How do I tell a computer an element of Thompson's group? One of the things I could just write it as a word in x x0 inverse and x1 inverse, but there are lots of other ways. I could, for example, just simply tell it, here are the 5 breakpoints. They're all rational numbers, so I can write those into the computer and it will understand it. Here are the slopes in between, right? There are, again, rational numbers, so I can type those in. On the other hand, it would be a lot harder for me to tell that to a computer. In particular, how do you even just tell an arbitrary real number to a computer? Can't be done, right? Take a transcendental number, right? It's not something that's not even a root of a polynomial or any, I mean, just sort of, there isn't a way to do that in general. Okay, but for Thompson's group F, there are lots of ways to do this. Okay, so I want to talk about 4 algorithms for these groups. Algorithm number 1 is the word problem. So the word problem just says, give me a word in x0, x1, and so on. Or if I'm just looking at finitely generated subgroups of PL plus I, give me a word in that finite generating set somehow. And I want the algorithm to say yes or no whether that word represents the identity or not. Okay, so if that subset came from inside of Thompson's group F, I'd be golden. The answer is that there are algorithms to do that. There are actually a lot of different algorithms, just that there are a lot of different ways to present elements to a computer. For an arbitrary finite set of homeomorphisms, what do I want to do to solve the word problem? Well, these homeomorphisms are just functions from the unit interval to the unit interval. They're just lines. They're linear functions. What am I going to do to figure out whether a word represents the identity? I'm just going to multiply the functions. Well, again, I'll point to my little picture over there and say, yeah, but how does a computer do it if you haven't even been able to tell it the slopes or the breakpoints because they're not nice rational numbers? Okay, so anytime a computer can determine the breakpoints, you have a way to tell the computer about it, even, square root of 2, pi, whatever. So you have some way of telling the computer about it. If it can determine the breakpoints, find the slopes to left and right of breakpoints, multiply slopes and so on, whatever it needs to do in order to multiply the functions, then we'll be able to solve the word problem. Okay, so what I really want to do is look inside of PL plus I and figure out some notion of what it means to be a computable subgroup. Okay, so I'm now going to give you, right. Before I can tell you what a computable subgroup is, I need one more piece of notation. Okay, so for any subgroup of PL plus I, any element in PL plus I can draw the graph of that element, and then I just worry about where are all the pieces of the graph where the graph doesn't follow the diagonal, doesn't follow the identity map. And what I want to do is just define separate functions for each of those. So the function h1 does this and then does the identity all the rest of the way. And the function h2 does this and does the identity before and after and so on. Those three functions will commute, and their product will be the original function that I started with. Okay, so those things are called the one-bump factors of the group element G I started with. And generally speaking, most of the time when you're looking at subgroups of Thompson's group or subgroups of PL plus I, what you want to do is look at the group generated by the one-bump factors. Yeah?
Just a clarification, the group operation here is composition of functions?
Yes, that's exactly right. Yeah. Yep. Okay, so there's a theorem of Gilly-Golan, who is not in the room, who is one of the postdocs. Oh gosh, okay. Anyway, so one of the postdocs who's participating in the program right now proves that if you take, so this is called the split group because we split this thing into its one-bump factors. The split group of a split group is the split group, right? If you take the one-bump factors of what you got inside of this group, you don't get anything new. Okay, so I'm going to use this to define the notion of computable. All right, so I want to talk about when a subgroup of PL plus I is computable, and let me say that I don't expect you to remember all of that verbiage. It's up there so that you have the comfort of knowing that there was some kind of sensible something. But really the thing to remember is you can do the computations that you would think you would want to do in order to be able to multiply homeomorphisms, piecewise linear homeomorphisms. So you want to be able to multiply and invert elements, but in the split group. You want to be able to determine breakpoints, compute slopes at before and after endpoints, multiply and invert elements in the group of slopes. So you might have, let's see, maybe I'll come over here. You might have a couple of elements. Ooh, I have all kinds of color here. Okay, so you might have at some point more than one element. You might even have 5 elements that sort of branch off from the identity at the same breakpoint along here. And so you want to be able to look at the set of all the slopes that occur and figure out just as a group, and by a group I really just mean group of real numbers with multiplication, sort of figure out as a group you want to be able to multiply those. You want to be able to understand whether that group is finitely generated or not, all that. Sort of, in some sense, sensible computations along those lines. Okay, so if you've got a computable group, anytime you have a finite subset of that group, it's going to generate a computable group in its own right. And for any finite subset, the group generated by that subset will have solvable word problem. In particular, Thompson's group is a computable group. It had that generating set with x0 and x1, so it's already a finitely generated one. And Thompson's group has solvable word problem. Yeah?
So how does a computer determine whether the group is discrete?
Okay, so for example, if we're in Thompson's group, so all the slopes are a power of 2, it can determine whether or, how do I say this? Okay, so in particular, what we want to be able to do is figure out what the least slope is greater than 1, but you can't get anywhere between 2 and 1. Right? So for some groups, it's just automatic without having to think about it. Yeah. So I'm not really saying that I have an algorithm to do that. I'm saying if I've got a way to do that. Yeah. Yeah. Okay. So that's algorithm number 1. Right? The word problem worked. Basically, life is good for the word problem. So what do? You ramp up the word problem to the subgroup membership problem. So I want to still have a finite subset of a computable group and take a look at the group that it generates. So a nice finitely generated computable group. And I have a subgroup and a subgroup, H, inside of there. And the H subgroup membership problem says, is there an algorithm that upon input of a word of the generators of the bigger groups, the generators S, tells me whether or not that word represented something in H or not? Okay, so the word problem is just a special case of this where you're doing this where the group H is the identity. Okay, so the question is, how about now? Do we still have a solution to this? Do we have an algorithm that works? Okay, so Gubin's up here proved that for Thompson's group F, if my subgroup H is both finitely generated and already split, it's equal to its split group, then yes, there is a solution to the subgroup membership problem. But in general, nobody has a clue. Okay, so what Colin, Blake, Tara, Bro, and I proved is that if you start with a finitely generated computable subgroup of PL plus I, and it's generated by a bunch of one-bound functions that are in what I'm going to call general position and not explain to you for a while yet, then again, we've got a solution to the subgroup membership problem. But I will mention that that general position implies, again, that H has to be the split group. So we don't have something, a bigger set for Thompson's group, but we have something for computable subgroups of PL plus I now. But we also have an extra restriction that the group has to be solvable. I don't want to assume people know what solvable is. How many people in the room know what actually, maybe how many people don't know what solvable is? Fair number. Okay, so next slide's all about that. For now, I'll just say it's an extra algebraic condition. But it's already, we're only on algorithm number 2, algorithmic question number 2, and we're already, in some sense, getting to big swaths of unknown knowledge, right? So we've got, for lots of subgroups of Thompson's group F, nobody knows whether the subgroup membership problem is solvable. Okay, so a group is solvable if I can write a finite sequence of subgroups, each one normal and the next one up, every quotient being abelian. Okay, so one example of this is the Heisenberg group. So this is the set of integer matrices, upper triangular with a diagonal all ones, which turns out to be a semi-direct product of z squared and z. So it's solvable. I'm going to show you another example that looks perhaps a lot more complicated, and you're going to wonder why I'm doing this, but it will be relevant. So this is called the wreath product of z with z. So I'm going to have an integer's worth of copies of z, and I'm going to take a semi-direct product of that with z. So each of these z's is generated by xn, and this z is generated by t. And so each of the xn's commutes with all the others, and t conjugates xn to xn plus 1. It just moves things up the line. Okay, so this thing is finitely generated. It's actually finitely generated by by x naught and t, but it's not finitely presented. Okay, but the thing to notice is that this nice, lovely, finitely presented group is not a subgroup of PL plus I at all, much less Thompson's group, but this guy is. In fact, this is kind of the model for what all the solvable subgroups of PL plus I look like. They look like iterations of doing this wreath product and taking direct sums, and then do another wreath product with z and take more direct sums, and just keep going. Okay, so when in doubt, when you can't solve a problem, try a harder problem. Yeah, okay. But that is what I'm going to do. So this is ramping up to something harder yet. So this is the uniform subgroup membership problem. So before, the old subgroup membership problem was for a fixed subgroup. I was just going to put in words, say, are you in that group? This time I'm going to throw in a finite set of words and one more, and say, is that one more in the subgroup generated by the finite set? Right? So I'm inputting both the subgroup and the word and saying, what happens? Okay, so this is completely unknown for Thompson's group and many other, and basically just about any other computable subgroup of PL plus I you could think of. Okay, so, but one idea of how to approach solving this uniform subgroup membership problem, how would you sort of envision building an algorithm, building a software package? Well, the first thing you might want to do after these words are input is sort of try to figure out, is the group generated by these guys solvable? And if it is, then you're going to go do this algorithm over here. And if it's not, then you're going to go do this algorithm over here, because they are very, very different looking cases. Okay, so question is there a gatekeeper? Is there an algorithm that does that gatekeeping and knows how to send things each way? Well, that's the solvability recognition problem. So this is the problem that says you have your finitely generated computable subgroup of PL plus I, and asks, is there an algorithm that upon input of any set of words over the generating set can determine whether that's the subgroup that they generate is solvable or not? And the answer is yes. That piece, at least, there is an algorithm to do. You can recognize this. Okay, so I've now finished the first, what looks like 2/3, it's actually about half, of the talk. So we've talked about the two groups, we've talked about the 4 algorithmic questions, and what I really want to do, I'll back up just for a moment, what I really want to do is talk just for the rest of the time about pieces of this algorithm, why it ought to work, and how it works. Okay, so the first piece of the puzzle is a theorem that says if I've got a finite set of homeomorphisms, piecewise linear homeomorphisms, notice I'm not saying anything about the word computable here. This is just true for any finite set of homeomorphisms in PL plus I. If I've got a finite set and the group that they generate is solvable, then I can actually figure out a bound on that tower. Remember the normal subgroups, G0 normal and G1 normal and G2, right? I can find a bound on the length of that tower. Okay, so if you remember, for Thompson's group F, for example, we had, I've lost white. I must have taken the only white away. So Thompson's group F had these two generators, x0 and x1. There they are. If I count the total number of breakpoints that appear in those two generators, it's 1, 2, 3, 4, whoops, 1, 2, 3, 4, 5, 6, 7, 8. That was wrong. 1, 2, 3, 4. 1, 2, 3, 4, 5. That was correct. Okay. All right. You know, if you start pointing enough times, eventually you just get up to whatever number you want. Okay, so 9 breakpoints. So if this is going to be solvable, it has to be the case that any time I find a sequence of subgroups, starting from the identity and going up to Thompson's group F, where each of the quotients is abelian, I've got to be able to do it in 9 steps. I can't do it, I've got to be able to do it in 9 steps. Okay, well the answer is actually Thompson's group F is not solvable. And so if I start building subgroups inside, I will end up finding an infinite sequence and no sequence of length 9. Okay, why is this a key piece of the puzzle? Well, the solvability recognition problem algorithm is genuinely an algorithm. So this algorithm is going to halt in a finite amount of time, no matter whether the answer is yes, it's solvable, or no, it's not. To halt and say yes, you're solvable, you just have to have found this finite sequence of subgroups. So that's, I think, probably a bit more plausible that you might be able to do that in a finite amount of time. But to say no, it's not solvable, you need to be able to know at some point in a finite amount of time you've gotten too much, you've gone too far, and if it was going to be solvable you had to have found out by now. And it's this bound right here that gets that direction to stop. It's this bound that allows us to say no, it's not solvable in a finite amount of time. Okay, there are a couple of key ingredients that went into, well, sort of the proof of that, but also the rest of the algorithm that I want to mention also. So this is, start with the theorem of Collin-Blake's that says, for any subgroup of PL plus I, that subgroup is solvable if and only if its split group is solvable. So pretty much all the time we really just want to deal with the split group because it's just easier. We have these nice little one-bump functions running all over the place that we can use. Okay, the other piece of this is another theorem of Collin-Blake's that says if the split group contains an infinite sequence of one-bump functions that look like this, right? So the support of this, it's only got one bump, otherwise it's just along the identity. This next one is, again, a one bump, it's on the identity otherwise. If the supports just keep getting strictly smaller, doesn't have to get strictly smaller on both sides, but strictly smaller on at least one side, then the group can't be solvable if it's got an infinite tower that looks like this. Okay, so my plan for what I want to prove to you, in some sense, is I want to prove that we can recognize who's solvable and who's not when my generating set contains of 2 one-bump functions and nothing else. Okay, so just a very special case. So let me back up. A special seeming case. In fact, it's going to contain all the information that we need for anything. Okay, so I'm going to start with 2 one-bump functions f and g. Well, if I just look at the bumps, there are only 5 different ways that their bumps can interact with each other. Either there's no overlap like this, or they overlap a bit more, or the one's contained in the, right? There's not many options. There are 5 in all. And I'm just going to give you the 5 different options in turn. Okay, so this one is they have no overlap at all. Well, these 2 elements of PL plus I commute. If I do this one first and then this one to a point, if I act on this and a point over here, this function will map that point to something still in this interval, right, less than this number, and G will do nothing to it, or G did nothing to it and then I do F to it. Right? It just doesn't matter. These two commute. So abelian groups are solvable. They have a tower with length 1, so I'm solvable. Okay, option number 2 is I've got a one-sided overlap. Now this is exactly the picture I was talking about a few minutes ago, right? These are the two generators of Thompson's group, and they have exactly this kind of one-sided overlap. Okay, well, there's a lemma that you can prove about homeomorphisms that says if I take a look at what happens to G inverse FG, the support, the places where this function is away from the diagonal, is just the same as the support of F acted on by G. So another way of saying this, if I start with F, oh, I should say, using notation here, F to the G means G inverse FG, and so F to the G squared is G to the minus 2 FG squared, and so on. Okay, so if I look at G inverse FG, what's going to happen is that this point moves up because G is up above the line. That says that a point here, a point directly under him, he's going to map to something about here. So this isn't a terribly believable picture at the moment. But the point is that it's going to move this point somewhere further up the line, but it's not going to move that one at all. So I'm going to end up with an infinite tower in the end. If I just keep conjugating by G and then by G and by G, I get one of these infinite towers. And what Colin Blake had shown was that anytime you've got an infinite tower, you're not solvable. So for this configuration, definitely not solvable. Okay, how about if I've got a chain? I've got this picture. Okay, well, this time what I'm going to do is take a look at F and G inverse FG. What's going to happen there? Well, again, G inverse FG, it's not going to shift that endpoint at all, but it's going to move this one up here, and I'm going to end up with a one-sided overlap. And we just said one-sided overlaps gave you not solvable, so we've got to be not solvable. Okay, option 4. Now we're getting to the more complicated ones that I put off till the end. Okay, option number 4 has a couple of cases to it. So first of all, option number 4 is I've got the support of F strictly contained in the support of G, right? No sharing an end of any sort. Okay, so what I really want to do now is take a look at what happens when I take F, the smaller guy, and conjugate him by G. And what's going to happen is either I'm going to end up with moving just a little bit, in which case I will have a chain. And if I have a chain, back in part 3 from the previous slide, I know that I'm not solvable. The other option is that somehow this ends up completely disjoint from where F was. And then conjugating by G again will make this completely disjoint, and so on. So I'll just have a copy of, if I conjugate by G inverse, I'll go this way. I'll just end up with a bunch of bumps with all the different conjugates. Well, that's exactly the setup that you need to do Z-Ruth product Z. Right? So each one of these guys is going to copy, so F and G conjugated, F conjugated by G and F conjugated by G inverse and so on. Each one of those is going to generate an integer subgroup. These subgroups all commute because their support's all separate. And the conjugation by G just takes the generator of this guy to the generator of this, and then the generator of this to the generator of this. So we get Z re Z. But that's a semi-direct product of something huge but abelian with something abelian. So we actually are in the solvable case at that point. Okay, so everybody okay up to here? Very much proof by picture here. Okay. All right, last case, number 5. Number 5 says, what happens if they share both endpoints? Okay, so this was, in some sense, the hard scenario that we were talking about a little while ago. But let me make this actually share both endpoints. Maybe I will use the one that's a bit more forward too. Okay, so option 1. There's somebody nice. And option 2, maybe green. Oops, can't go too high because I need to end up there. Okay, so F is pink, G is green. I can understand why G is green. I don't know how to make F pink, but there it is. F and P, they're so closely connected, right? Okay, so what am I going to worry about? Again, I'm going to divide this up into cases. And the cases that I need to worry about is what happens if, so what happens, oh, let me mark A and B and things like this. Here's A, here's B. I want to look at the derivative of F at A coming in from the right, right? That's what F plus of A means. So I want to look at the slope of F coming in from the right, and I want to look at the slope of G coming in from the right. And I say, are they common multiples of some other number? Right? Is there an integer k and an integer l such that F and k, k times the slope at F and L times the slope at, is there a number c such that k times c is the slope of F and L times c is the slope of G? But I need that happening over here at the same time with the same integers. Right? So I need a common slope here so that k times that integer is the slope of F coming into B from the left, and L times that integer is the slope of G coming into B from the left. Okay, if that's true, then I still need to worry about, I want to say this. If that's true, then what I want to do is just take a look at, I say this, I will just boldly claim it and draw it. Purple maybe? Ah, purple should, no. Anyway, still don't know how to get F to be pink even with purple. Okay, so the idea here is that if there is such a number c, such a slope c, where this is an integer multiple of that slope and that's an integer multiple of that slope, then I should be able to find elements, an element that I can build by taking powers of F and G that have those two integer slopes for the number that those were multiples of somehow. And I'll call that C. Okay, so then what am I going to do? Well, what I'm going to say is, well, F times a certain multiple of C is now going to be a smaller guy. He's actually going to be a little bump in here. So this is going to be F times C to the minus K. Because basically what have I done? I've just made it so that the slope coming into this right to the right of A, I've just forced it to be 1. And if I do the same thing for G, I'm going to get another little bump somewhere, G times C to the minus L, because I've somehow negated its slopes. Okay, so now the subgroup generated by F and G is also generated by C and these two guys. But now I've got the setup from case 4, where I've got this big guy, the guy with the big support, and then I've got little guys inside who support strictly contained inside. No one side or the other kind of thing. Okay, so then what am I going to do? I'm going to start looking at conjugates and deciding, do I get chains? Do I end up with one-sided overlaps between a conjugate of him and a conjugate of him? I basically need to just use his cases 1, 2, 3, and 4, the previous cases, to figure out whether I'm solvable or not. On the other hand, if there's no way to build this, if the slopes didn't satisfy some nice property like that, I couldn't have been solvable. It won't happen again. I'll be able to come up with an infinite tower of some sort. Okay, so that's the situation for 2 one-bump functions. Okay, well, as it turns out, that's the situation for all finitely generated subgroups of computable subgroups of PL plus I. So the following are equivalent for any finitely generated group, actually finitely generated subgroup of PL plus I, not even computable, just any finitely generated subgroup. If you're solvable, you can't contain a chain. Sorry, your split group can't contain a chain. So just look at all of one-bump factors of all of your elements and see if you've got this picture somewhere. If you do, you're not solvable. If you don't, you're solvable. Same thing for the one-sided overlap in the split group, and same thing for containing a tower. Solvability means you can't contain any of these things, and it means exactly that. If you don't, you are solvable. Okay, so the last piece of this is just talking about, now that we've got this, talking about how the solvability recognition problem works. So essentially what we're going to do is just keep looking for these chains and the one-sided overlaps. So remember, in a computable group, the computer can find the breakpoints, it can compute the slopes, it can decide which slope is bigger than the other. So it knows who's under who. Okay, and as it's going along, it's going to build deeper towers, right? As the computer is trying to figure out, do I have something solvable or not? Anytime it finds things in pairs of bumps from the generators that were in case 5, there's an algorithm to build this C function and these 2 smaller bumps from it. And so it's going to build essentially what we've just built here with C and F times C to the minus K is a piece of a tower, right? We're trying to go deeper and deeper. So this algorithm is going to, anytime it lands in situation 5, build a deeper tower. Otherwise, it's going to be in cases 1 through 4 and know the answer. And anytime it's stuck, it's because it's in situation 5, so it builds yet another layer to the tower. And if it ever gets to the point where it has built a tower that's greater than the number of breakpoints in the original generating set, so greater than 9 for Thompson's group, for example, it knows for sure and for certain that the thing's not solvable. But if it ends up getting to a point where it has no more towers to build, in case 5, it only lands in 5A and not in, it only lands in 5B and not in 5A. It's not building more tower. Well, in 5B, we know the answer again. So anytime that it's not got a tower to build anymore, and it's landed in cases 1 through 4, it knows how to find the answer. Okay, and that's it. That's the algorithm, and that's my talk.